It's a pleasure to welcome Pragya. So we heard a lot about galaxies and stars in the previous talk. Well, let me introduce another star. She's not light years away, but she's here in Cambridge, Massachusetts, at another university, Harvard, yes. So she received a PhD in statistics from Stanford University in 2019 with Immanuel Candace, and her dissertation was recognized by Theodore Anderson's Theory of Statistics Dissertation Award and Rick Wayland Graduate Fellowship in Humanities and Sciences. And her research broadly spans high-dimensional statistics, statistical machine learning, robust inference, and prediction. She's known especially for her impactful work on modern maximum likelihood theory for high-dimensional logistic regression, her work on fairness, and her work on interpolation, a subject that she will discuss today. Please welcome Pragya.
Thanks so much, Sasha. Mic has set in? Yeah, OK. So thank you, everyone, for sticking around till the end of the day today. It's my pleasure to be speaking to this audience, and thanks for the invitation. And I'll also say this is a crazily intimidating position to be in after the really fascinating talks we heard since the morning. So thanks to all my co-speakers for the really inspiring talks. So maybe let's see if I can close this session and rise up to the standards. So today, I'm going to talk to you about two central objects in machine learning. So the first object is what is known as min-norm interpolation. So what are interpolators? These are classifiers or regression functions that achieve zero training error. And min-norm interpolators are just a special kind of interpolators, which we'll talk about today. Min-norm interpolators have been sort of the real big deal in machine learning theory in the past few years. But together with that, new hot stuff in town, I'll actually talk about AdaBoost, which is a more classical machine learning algorithm introduced in the mid-90s, and indeed a very celebrated ensemble learning algorithm. Now, what we will do is there's a well-known connection between these two things, and we will take a high-dimensional statistics viewpoint on this connection and uncover some new phenomena about both the interpolators and AdaBoost. So obviously, today started with Mike Jordan, for whose talk it's always inspiring. And I don't have the really wonderful triangle that he drew connecting three subfields, statistics, computer science, and economics. But if you do want to think of this work as sitting between two different fields or subfields, then I would say the way to think about it is high-dimensional statistics meets statistical machine learning. OK, so let's dive right in. The main motivation for this work is to understand three phenomena in machine learning that has really driven everybody's curiosity. So the first phenomenon is that of benign overfitting. And it's known under many different names. So let me describe what it is. Most of you know what it is. So we commonly observe in modern machine learning systems that they can interpolate the training data, achieving zero training error, but often that does not harm their generalization performance. So it's overfitting to the training data, but the overfitting is actually benign. State-of-the-art neural networks have been known to be of this form. Today, we will see that this is a not-so-modern phenomenon in the sense that this was already known in the context of the boosting literature in the 90s. The other thing that has been really fascinating to see everywhere in the literature is the implicit bias of popular machine learning algorithms. So suppose we are in a setting where you can, whether a regression or a classification or a prediction problem, suppose you can find a perfect classifier, meaning you can drive the training error to zero. Now, when you can do this, often you can find infinitely many such perfect classifiers. But what happens is when you run popular machine learning algorithms, they will actually end up choosing a very special one from this infinitely many choices of interpolating the training data. So that's the phenomenon known as implicit bias, meaning that when you start the algorithm, for instance, if you're running gradient descent, when you're starting the algorithm, it's not explicitly regularized towards any special solution. But it is found that if you choose things like initialization and learning rate and so on properly, the algorithm, when it sort of converges, it's going to pick a special classifier. And because it picks the special classifier, it turns out that it really picks the classifiers which are going to generalize well. So in that sense, it has an implicit bias that it's not explicitly regularized, but there's an implicit regularization. And this is very interesting because of course, part of it helps explain why these algorithms are working well in practice in terms of generalization, because it's picking the special classifiers. But it's also important because these algorithms are extremely complex. So it's very hard to track them analytically. It's very hard to study their properties directly. It's very hard to build a theory for them and understand what they're actually doing. However, if you know of their implicit bias, you can turn your attention, study these special classifiers, and then whatever you understand about these classifiers, you can transport that in your algorithm land, and that should tell you more about your algorithm. And that's something that we are going to use in this work. And the final vignette in this talk throughout will be to understand the role of overparameterization, both in the context of generalization and optimization. One thing that has been observed in modern machine learning empirically in the context of neural networks in particular is often overparameterization helps optimization, meaning that in overparameterized settings, sometimes you actually optimize faster. But it's not true that all of these phenomena are completely understood. So today, we are going to shift our focus from neural networks, which have been very popular in recent times, but go back and revisit this celebrated ensemble learning algorithm, AdaBoost, and we'll try to understand these objects in the context of AdaBoost. We'll see that the tools we need to build to understand this is actually eventually going to help us also for other algorithms, and I'll talk about that a bit. OK, so let's dive right in. Quick recap or detour into understanding what has been known in boosting so far. So boosting, by now, it is a general term that refers to the problem of producing a very accurate prediction rule by combining rough and moderately inaccurate rules of thumb. So what do we mean by rough and moderately inaccurate? These rules of thumb only need to be a little bit better than random guessing. But boosting generally refers to the approach where you take many of these weak classifiers and smartly aggregate them and come up with an eventual prediction pipeline, which works well in practice. And this literature goes back to the works of Valiant in '84. One of the earliest algorithms were introduced by Shapir, Freund. And then eventually, there was this major breakthrough through the AdaBoost algorithm, which was introduced around 95, 96. So this is sort of almost a snapshot from a part of their paper, rewritten in the context of our work, but quickly describing what this algorithm does. My recommendation will not be to read through the math, but more like the 2 lines of words. This is an algorithm which takes in your training data. It maintains a set of weights on your training data points. So maybe you initialize with uniform weights. So that is 8 and naught. So I've given just, if I have n data points, just give 1/n weights on each of them at the beginning. And then at each iteration, AdaBoost is going to choose a classifier. Here I have represented it through a very simple one. It just chooses the best possible direction in the sense of this maximizing the absolute weighted correlation. So you choose a classifier, and then you do 2 things. One, you define an adaptive step size, and second, you define adaptive weights. So what's the step size? In this formulation of the algorithm, we are maintaining these iterates, theta t. So we have to update that every time. And then what you do is, if the classifier at this iteration was a good classifier in the sense that your error is kind of low, you take a large step in that good direction, and vice versa. If it was not so good, you take a small step in that direction. And then you next update the weights on your training data, also adaptively. So what you do is the following. So you take a training data point, and you look at the classifier at this iteration. Now, if you classified this data point poorly, for the next iteration, you upweigh that training data point. And if you classified it well, this time you downweigh that for the next time. So basically what it's doing is it's looking at what parts of the space am I classifying well in this particular iteration. I'm going to downweigh those good parts because I've already learned them. I'm going to downweigh them for the next time and upweigh the harder parts. So that's sort of the idea. Now, this is a very classical algorithm. And the reason why this became very popular because this is one of the earlier emergences of a plot that we see a lot these days, but that challenges the classical bias variance trade-off diagrams in statistical learning. So this plot is basically AdaBoost run on a data set. X-axis is the iteration time. And as you see, the training error drops to 0 very soon, but the generalization error continues to drop way beyond that point, right? And so this naturally piqued the interest of statisticians, machine learners, across both the communities, computer scientists. And many explanations emerged for why this is happening. So one of the explanations that was put forward is based on what is known as the margin theory. So I'm going to define a quantity. If I have a classifier, let's represent a general classifier by the function f. So let's restrict to a binary classification problem for this talk. So the response or outcome variable is just a plus or minus 1. Then the margin of any training data point for this classifier f is just given by the product of yi times f of xi. So what was observed in this seminal work by Shapiro et al. Is the curve on the right-hand side above. They are plotting what's known as the empirical margin distribution. And they're plotting that over the course of iterations of AdaBoost. So if you look at that curve at time t equals 5, you actually see that not that many points have a very high margin. But if you look at the curve when the iteration time is much higher, like 100 or 1,000, then you see this sort of a nice curve which sort of peaks around 0.8, and there is a sharp rise. What that actually tells you is by the time you're at time point 100, a large fraction of your data points actually have a large margin. And further, between time 100 to 1,000, the margin distribution, that actually stabilizes. And this, if you contrast with the picture on the left, you will see that the generalization error has almost stabilized by time 100 and sort of stays stabilized after that. So this was sort of their proposal. They said that this empirical margin distribution is the key quantity. What it does mirrors the generalization error curve. So this explains basically this whole benign overfitting stuff. OK. And these interpolators have been studied a lot in recent times. Obviously, you can't just show pictures and then claim a new theory. So they have guarantees which try to back this theory. What the guarantees say roughly is the following, that if you look at your prediction error on a new test point, you can upper bound that quantity by lots of terms. But the thing to note is the first term here is based on the empirical margin that I just showed in the earlier slide. And in the other terms, a threshold shows up. For instance, kappa here is a very arbitrary threshold. So for any positive kappa, you have an upper bound of this form. All right, cool. So in the upper bound, the empirical margin does show up. But what you can ask is the upper bound has a free parameter. And can I optimize that as a function of the free parameter? Because if I could optimize the upper bound, I can potentially make it much lower than what it should be for any free parameter. One way to optimize that is, let's look at the first term. So that's what we have. There is an indicator. So that's a 1 or 0, and there is an average. So the least value that can take is 0. So we can just drive the first term to 0. OK? So we are trying to figure out, OK, how do we drive the first term to 0? Now, one way of doing that is by taking a choice for the threshold of this form. So the thing here below that I've defined, that is a quantity that's known as the max-min margin. So what it is doing is it's taking all linear classifiers of this form xi transpose theta. It's normalizing them by their L1 norm. And then if you take minimum over this quantity for all your data points, just that is going to drive the first term in the upper bound to 0. That's because on the left-hand side, I have yi times f of xi. So if I take the minimum of all of this on the right, I have a strict inequality. It's going to drive it to 0, just taking the minimum. But then the interesting thing is, I took this for any possible linear classifier. So theta is actually free. So then you can take a worst case over all possible choices of theta. Now, why do you want to take a worst case? Because if in the upper bound, if you look at the second term, the same threshold kappa shows up in the denominator. So to drive the denominator lower, you actually want to have a higher value of kappa. And because theta was free, you can take max over all possible theta. So that's sort of one of the motivations in this context to look at this max-min margin. And now once you have this, it immediately raises a debate. That is, which quantity is actually key to generalization, right? So in the upper bound, we have the empirical margin. But now I can rewrite this upper bound with a different one, the one that is below. And there, this max-min margin shows up. And Leo Breiman has written about this quite a lot. And he's known to have advocated for, max-min margin seems like the key quantity for generalization and not the empirical margin. But because we have upper bounds in both these cases, we can't really resolve this debate without more precise characterization. And that's something even was alluded to in the Shapiro et al. Original paper. So in this talk, we'll try to understand which of these is fundamental in the context of AdaBoost. Now we come to the other phenomenon I talked about at the beginning, that is, does this algorithm have an implicit bias? And it turns out it does. and that has been well understood. And the implicit bias of this algorithm is in the direction of these things which are known as min-norm interpolators. So let me now introduce formally what this is. So we are in this binary classification setting for today's talk, and if you have data that has been labeled in two different ways, plus and minus ones, there can be geometric situations where you can perfectly separate the data using linear hyperplanes. So this is sort of the picture I'm showing here. So maybe the blue points are the plus ones and the red points are the minus ones. If you can do this, then the data is called linearly separable. And for linearly separable data, there are many possible ways to separate it. Once it's linearly separable, I can have many hyperplanes passing through them, right? Now, if I take these choices for the hyperplane, so that's defined by xi transpose theta, I'm looking at just linear hyperplanes, then, and if I take a minimum norm for all possible theta that's going to separate, that's called a min-norm interpolating classifier. And the moment I have norms, I can plug in many different norms, right? I can plug in the L1 norm, L2 norm, any other LQ norm. So once we go to this land, we can have a whole host of these interpolants known as min-LP norm interpolants. For AdaBoost, just the L1 norm will be important. So why am I introducing this? I'm introducing this so that I can introduce this famous result due to Zhang and Yu and Rosset et al. Later, Telgarsky has worked on this stuff. That says the following. If you have linearly separable data, if you run AdaBoost, and then you have certain limiting conditions in the sense that if you take infinite small step size, you take step size going to 0. You take infinite time limit, you just keep on running the algorithm, take time going to infinity. Then your AdaBoost iterates, normalized in L1 norm, they are going to converge in direction to one of these interpolants, okay? And one of the min L1 norm interpolants. So this means that this is the implicit bias of the algorithm. And it means that if I can understand the interpolants well, and if I can quantify this statement instead of having a limit, if I can have a finite sample version of this statement, then we can directly just study the interpolants and understand more about the algorithm. Now, why is this related to what I presented before? That's because these interpolants and the margins, and they're all tied together. So for instance, the max-min margin, which just showed up in the previous slide, if I solve that max-min L1 margin problem, as a solution, you will get one of these interpolators. So these are equivalent. They're not like separate from each other. So that means that this L1 stuff seems pretty important for AdaBoost. The min L1 norm interpolant shows up as the implicit bias. The max-min L1 margin shows up in upper bounds for generalization error. And even more, so this is an algorithm. For that, you might be interested in studying what is the optimization speed of the algorithm, or what is the number of steps it takes for the algorithm to achieve zero training error, questions of this form. And in that context also, there are sort of classical results due to Freund and Shapir and later Zhang and Yu, which tells us that if you want to study how long it takes for an algorithm of this sort to have zero training error, you can also have upper bounds on the number of iterations using this max-min L1 margin. So it shows up in the denominator, the square of the margin. And there are other factors which are not so important. Fine. So what all this tells us is that it seems that this min-norm interpolant and the max margin are very crucial for understanding AdaBoost. And so that will be our goal today. So this is some of the prior work. What we're going to do today is we're going to revisit the empirical margin versus max-min margin debate. Then we are going to take a tour into understanding the max-min margins and interpolants better. And to do that, we'll ask questions of the form, OK, exactly how large is the margin? What are the properties of the interpolant? And then what we're going to do is, instead of having an implicit bias result like it was in the previous literature, we're going to try to characterize in a more quantitative way how long it takes for AdaBoost to reach this min-norm interpolant. And we will see that if one can do that, if one can make a result of that form quantitative, then you can read off things like generalization error for AdaBoost, or things like what are the effects of overparameterization on the optimization properties of the algorithm. Okay? So that's our goal today, to understand these phenomena in the context of AdaBoost, and we're going to do that in a high-dimensional setting. As I said at the beginning, this talk could be viewed as high-dimensional statistics meets statistical machine learning. So when I say high-dimensional statistics, it's a really broad field, and many different people have contributed in that field. Many of them are in the audience today. I'll sort of go along a specific vignette of that field, which will give me very precise answers, meaning that I'll not have upper bounds, I'll have exact results in a limiting sense. But you'll see that that comes at a cost, that you need some modeling assumptions. And I'll start with the most toy model you could think of, and you shouldn't believe the model at all. But at the end, I'll say, what are the other settings where you can generalize and go beyond those models, those toy models? And what are the parts of the result we actually expect to carry over in more general settings? OK, so when I dive into the main results section, I think perhaps the most important slide is this one, which tells us where is all of this coming from the technical front. Now, it turns out that this margin-based stuff that has been significantly studied in the machine learning literature, and it's not just the machine learning literature. Things like the margin has been important in some other literature as well. For instance, if you go to the statistical physics literature, the works by Gardner in 88, Sherbina and Tarozzi in 2003, these actually tell us stuff and conjectures and predictions about things related to the max L2 margin. And some of those results and others have been formalized recently by two groups of people, Montanari et al. From Stanford, and one of the authors from there is currently actually in MIT as a postdoc, and Deng et al. This is a group from sort of Caltech and later on other places. So L2 margin is very important because we know that gradient descent in certain settings converges to the min L2 norm interpolator. But L2, L1 geometries are very different. So for those of you who have worked on statistics questions, things like if you have a result for ridge regression, you can't directly transport that and say something about the lasso, right? Because the L1 penalty really looks very different than the L2 penalty. And that is sort of the same challenge here. The L1 penalty, the L1 geometry lacks strong convexity type features. So there is lots of non-trivial stuff you need to do even to make this jump from L2 to other geometries. So that's something that we do. So I'll be a bit fast in the next slide. I'll say that the setting we work in, the part of high-dimensional statistics, is what is known as this proportional asymptotics regime, where the number of features and the number of samples are both allowed to grow. And the number of features in our talk can be much larger than the number of samples. And that's OK. But this regime has been heavily studied in sort of the last 1 decade or more by various groups of people. So this is something that has been studied in random matrix theory a lot, something that's been studied in statistical physics for even longer than a decade, and by various other colleagues in statistics, information theory. So there are really, this is not an exhaustive list by any means. So the reason why this regime is interesting is because stuff about is asymptotics helpful came up in the earlier talks today, right? And my one-line answer, if I put on my practitioner's hat, is like, no, absolutely not. So then why do we care about asymptotics? If there are some asymptotics that actually have good finite sample performance, in the sense that when you take the asymptotic predictions and you apply it when you have maybe very moderate sized data, maybe a few hundred samples, and if you actually see your asymptotic theory predictions matching in finite samples, then OK, maybe if asymptotics help you prove the math, that's OK. You can still use it in practice. Now, the question is, does this regime give us that? It turns out this is a regime that actually does give us that. And that's going to be interesting. And I'll show you some plots as to how that works out. Now, once you're in any high-dimensional regime, what's sort of very important is you need to sort of abstract away what are the important features of your problem. Okay? So let's say the notation is not important. Let's say we are in something like a logistic regression model. I mean, we can do more than logistic regression here, but we have binary classification. Anything that is of the type of logistic regression where you have a link function that has some properties, continuous, non-decreasing, that's fine. Initially, I have heavy conditions on the covariates of the form looking like IID Gaussians, but we'll go beyond that later. If you have a setting like this, the key things are understanding things like what is the signal strength in your problem, okay? And there are other properties of the signal that you do need to understand. But it turns out that without assuming any conditions like sparsity on the underlying signal, so your signal can be sparse or it can be very distributed and weak, without assuming a condition of this sort, you can actually summarize this high-dimensional setting into 3 problem parameters, okay? So I'm writing out these problem parameters because you'll see that in our results, this sort of shows up a lot. So psi is basically the over-parameterization ratio. It's how many features you have compared to the number of samples. And rho is your signal strength. The exact form is not important. It's trying to capture what is the signal strength in the problem. And mu is something that becomes a bit technical, but that tries to capture other kinds of moment information of the underlying signal. Okay? So the crucial thing from this slide is just the last line, which is just saying there are important 3 problem parameters, and we characterize what these are. Now, once you characterize that, and for today's talk, I'm just going to be in this linear separable setting. In one of my earlier works, joint work with Emmanuel, we had characterized sort of when is data linearly separable under certain Gaussian models. And we had a precise characterization of when that happens. If I just showed you the picture here, I'll say that depending on the signal-to-noise ratio, that is rho, and the over-parameterization ratio, that is psi, so the rho, the SNR, the signal-to-noise ratio, that's on the y-axis, and the over-parameterization ratio is on the x-axis. Based on this, there is like an exact phase transition curve such that above the curve, the data is basically going to be linearly separable, and below it's not. And this is also tied to things like maximum likelihood theory in these models and statistics, but probably for this talk, that connection is unimportant. The important thing is we're just going to be above this phase transition curve for today's talk. OK, so what are the main contributions? The first contribution takes a form of this sort, that what happens to the maximum L1 margin. And the key thing is we characterize what happens in the limit. Such a result was done in the context of L2 margin by Montanari et al. And Deng et al. We do that for the L1 case. And the important thing is the limit is characterized by your problem parameters, and we can exactly pin down what they are. Okay? So the characterization I will not get into, but we basically understand what happens to this margin. Okay. Now, going to these simulations that I was saying, is this asymptotics and useful? Here, what I'm doing is the x-axis is the over-parameterization ratio. And there are 2 sets of points. It's a bit hard to see. But there are actually points of 2 colors here, blue and red. And if you can't see the red points, that's actually great news for me. That's sort of what we're going for here. So what are we doing? The blue points are the empirical version of the margin. And given any data set, I can compute, if it's a linearly separable data set, I can numerically compute what the margin is going to be. That's because you can do that by solving a linear programming problem. So those are the blue points. That's the empirical version. And the red points are the limit of this margin that our theory gives us. So that's something completely theoretical. And the point is, do they match? So this number of samples is 400. You can see that when you have a few hundred samples, even just there, the asymptotic theory is actually a good abstraction for what's happening in finite samples. And that's sort of the point for this picture. Now, why is this important? This is important because the margin is useful in our goal was to understand generalization error. So the margin is really useful in talking about what the interpolant is going to look like and what its generalization error is going to look like. So this is a formula. It's a math formula. It's not insightful at all. But there are 2 things that I have highlighted there. And they are actually 2 scalar objects. So you see that there are 2 coefficients on the right-hand side. There's a C1 star and a C2 star. And if I were to tell you the long version, yada, 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 it tells you how to find these constants. But what's important is actually the interpretation of these constants. So what we say is the generalization error has a formula. There are no upper bounds. It's an exact formula. But in the formula, there are 2 physical objects that are very important. So the first is the following. If you take your interpolators and project it in the direction of the true signal, the angle you get from this projection, that's related to this first scalar constant, C1 star, that shows up in the generalization error formula. And there is the other constant, C2 star. That is basically directly proportional to, if you do this projection and take the norm of the residual, then what you'll get is C2 star. So what we're really trying to do here is, OK, high dimensions is hard, right? And now I'm in high dimensions without assuming things like sparsity conditions, so it doesn't reduce effectively to any kind of low dimensional stuff. So what should our goal be? Our goal will be to understand, OK, what are the crucial low dimensional summaries that tell me everything about the behavior of the system? And here, we're trying to do exactly that. These two scalar constants, the angle and the norm, they basically govern the behavior of the system. You can read off things like what is the excess risk and stuff like that by just looking at these objects. OK, so back to boosting algorithms. That's what we started with. And I had told you at the beginning that AdaBoost is known to converge to the interpolant in a specific limiting sense. So this is sort of our main contribution on the boosting side. What we say here is the following. If you run the AdaBoost algorithm with a non-vanishing step size, with the proper choice of the step size, then there is a time point that we characterize precisely, such that for every iteration beyond that time point, your AdaBoost is effectively going to look like one of those min L1 norm interpolants. And when I say this, what do I mean? I mean that if I look at the min L1 margin of your data points, taking the AdaBoost classifier, then that properly scaled is going to be arbitrarily close to the margin of your interpolants, the limiting margin. So this, in some sense, you can view as a quantitative version, if you will, of those limiting results in the literature. Now, what is crucial? The first thing that's crucial is, OK, once I can make this kind of quantitative, I can go back to the classical generalization error bound, which is sort of the box at the top. And then we can look at our theoretical results on generalization error and compare these two, right? So in this plot, the x-axis is the over-parameterization ratio once again. So there's the ratio between number of features and number of samples. And what we are plotting, again, are those blue and red points. So for instance, if I compute the interpolator on my data, I can actually estimate the generalization error by running simulations when I know the simulation setting. So those are the blue points on the curve. And once again, the red points are what our theory says the error should be. And once again, you see that they match. The orange stuff is the upper bound from classical results, ignoring things like log factors and constants. We are sort of trying to be a bit generous here in the sense that the constants are going to blow up that bound. But even if you forget the log factors and constants, you'll sort of see a gap between these two. Now, you see another line, vertical line on the left side of the plot. What that line is saying that what you see on the left side of the line is something you should not believe. What that means is our results are only for linearly separable data. And when that separation happens, there is a specific threshold at which it happens. So that line characterizes what the threshold is for this particular simulation setting. So our results are for the right side of the line. And you see there the blue and red points match. On the left side, they don't match. And they're not supposed to match, because it doesn't make sense to talk about the margin really there. OK? So this is how our results compare to the classical bounds. You see a gap even after we leave out log factors and constants in the bound. But what's perhaps also interesting is we had a characterization of the time point, the number of iterations after which boosting is arbitrarily close to the interpolants. And if we look at that characterization, what we see numerically is the denominator here is being plotted against the over-parameterization ratio, and that's increasing. So what's happening is that time threshold is actually decreasing as the over-parameterization increases. So what that means is the more and more you're over-parameterized, the faster the algorithm is going to converge to one of these interpolants. And this is perhaps in the boosting literature one of the earliest instantiations of formally showing that over-parameterization is helping optimization in some sense. OK. So what next? As we saw that boosting has this nice implicit bias towards the min L1 norm interpolants. And I also talked about things like ridge, lasso. They are not the same. But that also means that ridge and any other LP norm is also not the same, right? Like L2 is all this nice. It has like strong convexity, right? But because we can make the jump from L2 to L1, we can make the jump to some other norms as well. So we can characterize things like min LQ norm interpolants for other norms. And then it turns out that we can also come up with variants of AdaBoost that converge to these other interpolants. So the original AdaBoost converges to the L1 norm case, but it's very easy to modify the AdaBoost algorithm and come up with other algorithms which converge to LQ norm interpolants. So it turns out, the details in the next slide is not so important, but it turns out for a host of other norms, you can generalize all of this. And then that opens sort of a new door where you can ask questions like, OK, then which version of AdaBoost should I use in practice? These are all these other norms, and we don't know, for instance, for high-dimensional data, which one is optimal and things like that. So these are questions you could ask coming up from our work. And I presented things with very toy models where we had IID Gaussians on the covariates, and that's not something that you should ever believe in. So the natural question is, OK, what are other settings? So the first other setting is, if you change this IID entry condition to having some covariance on the features, that's OK as long as the covariance has some special structure. So things like, this is something very that has been studied a lot in things like random matrix theory. That is, if you have spiked covariance model type things, then in a lot of these settings, you can generalize all of these results with proper changes to how things look like. Now, the other thing you shouldn't believe in is that, oh, yeah, the data did arise from something like a logistic regression. That just is too simplistic in some sense. So then what do? You start studying things like what happens if the model is misspecified, right? And now, obviously, talking about all possible misspecification is going to be increasingly hard. We here consider the simplest case, where you have missed a positive fraction of the relevant variables. This is something, we are not the only people to consider this in the context of the proportional asymptotics literature. So colleagues from Poulides et al. And then Montanari and his group, they have also looked at things like this for other problems in this literature. And turns out for these kinds of misspecifications, you can actually generalize all this stuff under some conditions. But probably the thing which, OK, we haven't proved this yet, but this is an interesting plot which says that there are two things I'm plotting. On the left side, I'm plotting the margin value. On the right side, I'm plotting sort of the excess error. There are two curves here. One is for a covariant matrix, which has IID Gaussian entries. And one is for a completely different covariant matrix, which has plus minus 1 entries with some probability. So it's a Rademacher model. And then you see that these quantities don't change across this. This is a universality phenomenon. Such phenomena have been quantified in various parts of probability theory and also in various parts of machine learning. So can you actually prove this in the sense that can you say that, oh, actually, I can study Gaussians and then extend the result to, let's say, any kind of sub-Gaussian tailed objects? So in this work, we proved a version of this. It's, again, a toy version of this conjecture. That is, if you have some observed data from a Gaussian model, but then you run things like AdaBoost, you run things like the margin, but you actually do that on some nonlinear transformation of the original covariate. So on the right side, setting 2, the AIs, the sigma is a nonlinear transformation, and the F is some random matrix that has been applied to your original covariates. So suppose we calculate things like the margin or run AdaBoost with this setting 2 model. Then if you take a corresponding setting 1 model, where you take your AIs and you linearize them, get rid of the nonlinear transformation, but you linearize them sort of very smartly. What does that mean? You linearize them so that the moments of BI and AI, they still match. Like the mean of AI and BI matches, the variance for AI and BI matches, and the way you do that is by having these coefficients in the linearization, which you pick in a way so that the moments are going to match. So the setting 1, the VIs, those are actually Gaussian. My ZIs are Gaussian, the XIs are Gaussian. So that's a Gaussian model. It's not like there is a mu naught, there's an intercept looking term, but that's a Gaussian model. And the setting 2, that's a non-Gaussian model because of the nonlinear transformation. And so we can show in this setting that if you calculate the margin properly scaled under both settings, they're going to have the same limit. So this is a form of a universality result. It's not the strongest universality result. But this is an instantiation that the Gaussian assumption doesn't matter as much. This result is also known as the Gaussian equivalence theorem and has been proved in, the setting 2 is the nonlinear random features model in machine learning literature. That's how it's known as. And it has been proved by other people it was used in like Hastie et al. And May and Montanari as a conjecture, and then it was proved in Hu and Liu, and it's been proved by others in various settings. So we are able to do this in the context of this max-min L1 margins. So that's kind of hopeful that there are instantiations where Gaussian really helps, and then you can go to non-Gaussian by proving a universality result. But of course, there are questions that are not fully answered yet. OK, so wrapping up, what I said in today's talk is, if you want to take away one thing from today's talk, that is the following, that there are tools in high-dimensional statistics and probability that really help us characterize or give precise characterizations of quantities we really care about in modern machine learning. So some of these quantities are in the form of these margins and interpolants. You can characterize their behavior. But you can also characterize things like generalization error, optimization speed of real machine learning algorithms that people often use. Okay? Now, and this is sort of one of the key points, that which norm you pick wasn't as important. But this opens the door to many further questions, and I am in the area. So if anybody is interested to chat about this, I'll be very happy to. Like, we didn't do something like comparing between the different interpolants, different geometries. And the other thing I promised that we're going to come back to neural networks. And it's known in that literature is if you take things like linear convolutional neural networks, linear convolutional networks of certain depth, then they have implicit biases related to min LQ norm interpolants and the depth of the network and which norm you're looking at, they are related. So being able to go over to these other norms should tell you new stuff about these kinds of networks. Okay? So yeah, right on time. So that's the reference. It's up on my webpage, and acknowledging funding to NSF-DMS, William F. Milton Fund, and Harvard CRCS. And this work was joined with my wonderful collaborator, Tengwan Liang, who's currently in UChicago. Thank you for your attention. Yeah. You can ask me later.
That it's not really a hidden property. It is the search process. You accidentally get onto these. It's like if you search a lot of Roman estimator, one of them is going to become like MLE, right? Then you discover that instead of thinking about, you could have thought about there is a model. There is a object function for which this is the algorithm to solve for it. But now you can really do the other way around.
Yeah.
Implicit property instead of explicit.
Yeah. So. I'll not go into my backup slides right now because I don't know exactly where that particular slide is. But it's a very interesting question. And I think as a statistician, I really just wondered about this when I was getting into this literature. So it turns out that there are ways to rewrite the original AdaBoost algorithm so that you're able to see a particular step where you're taking a min norm kind of thing. And so our proposal for algorithms which should converge to LP norms was just changing that step instead of an L1 norm to an LP norm. So if you write it that way, if you start thinking about it, it's sort of very clear. And in some of the proofs of the optimization steps also, you can see why, if there is an implicit bias, it should be in this direction. But to be honest, when I read the first paper, it wasn't absolutely clear that if I looked at the algorithm, I can say something like that. I think when people did research, they soon realized there should be a phenomenon like this. And of course, then it was characterized very soon after that. But I'm just saying, I don't know whether the first time it was created, whether it was created thinking of this implicit bias. But now if you go back and look at it, it's sort of clear this is what it should converge to.
Right, but that's my point. I don't think people explicitly try to, because in algorithm literature, you look at different algorithms, right? You see which one works, right?
Mm-hmm.
If you think that the other way around, if you knew what's the things to be maximized or solved, you
Yeah.
set up an equation.
Yeah.
Then that becomes explicit because that's what
I totally agree. But just one pointer, that is the way the algorithm came up really has nice connections to the online learning literature. And so it sort of came up from that story, but then you soon realize there's also this other, but that's my understanding. Like maybe when the algorithm came up, this is what was happening in the back of the page calculations, which were not published, right? So I can only say sort of like what I sort of understood just reading the papers, but yeah, I totally agree.
All right, in the interest of time, let's thank Pragya again for a wonderful.
Thank you.